from London, speaker, tabletop gamer, a geek, and as he wrote to us, tattooed, pierced, and bearded, the Gov on brighter command. So Ian, let's begin. Adopting Polyglot Flow.
Hey everybody, thanks for coming. All right, let's dig into this one. This doesn't say very much apart from the fact that I'm old, and the only point I ever really draw out is the one on the bottom, which is that although it requires an understandable amount of courage to come up and speak, I would encourage all of you to do it. You all have something to share and tell other people, and there is lots of fantastic opportunity once you get into speaking and traveling and speaking to other developers. So don't believe that I am significantly smarter than any of you. It's just that I happen to have had the right opportunities to do this a bit. I work on a .NET. Any .NET devs in the room? I work on an open source messaging framework for .NET called Brighter. We compete with Mass Transit and Service Bus. We're very friendly and hopefully quite welcoming. We also basically compete with Mediator. We have a kind of like in-memory version. So please do check us out. All right, what are we going to talk about today? I'll start off with an introduction. What do I mean by this idea of kind of polyglot and polyglot flow? Where does it come from? What we're trying to get at? Then I want to look at, when we do messaging, the difference between more than queues and streams, messaging versus eventing, series versus discrete eventing, a bit of a taxonomy of the kind of things that we're trying to do when we build event-driven architectures. I want to look then at how what we think about here influences the kind of way we think about building our applications. And then I'll look at a few other aspects that may govern how we think about what messaging middleware we want to use. But the idea is to give you some advice for making decisions about picking messaging frameworks. And ostensibly, my key point is that in about 2006, we got this idea called polyglot programming. It came from Neil Ford. Neil Ford basically said, we should use multiple programming languages because some languages have a better fit because of their properties when applied to problems than others. And that, in a sense, as we began to build service architectures, one opportunity Neil called out was the opportunity for us to think about using different languages for different problems. In about 2011, Martin Fowler extended this idea with the concept of polyglot persistence. He said, well, if we're going to have all these individual services, they may not all need to use the same type of database. Right. So just you take away where I currently am, we make extensive use of DynamoDB on Amazon because what we need in a lot of cases is a key value store to just basically store some data that's mainly transient to do with the user's order and be able to retrieve it by its identifier quite easily. We don't need relational data to do that. But in other places, we do need relational data. Right? So we tend to pick the type of store depending upon the use case that we have. And that's become less of a controversial idea over time. My argument is that we need to do the same thing when we think about middleware. That different middleware has different characteristics and properties, as different as a key value store or a relational database. And we need to basically have some thought about the type of middleware we're using. Too often I kind of see this model which is, we'll just use Kafka for everything, right? And that's a real problem. Okay. There are costs. So Tim Bray in 2014 said a polyglot program, there's a real cost to continuous widening of the base of knowledge a developer has to remain relevant, right? The problem with introducing multiple languages is that your developers suddenly have to know multiple languages in order to move them about. Similarly, Martin Fowler points out that there's a cost in complexity to polyglot persistence because now we need to understand how multiple technologies work. The pressure on my platform engineering department grows greater. And the same is also going to be true if we adopt Polyglot Flow because we have to now master more than one piece of middleware. Enough organizations have difficulty running Kafka. Start expanding that by getting them to run a whole lot of other ones, and that may be a struggle. And that tends to be probably the biggest bottleneck to this idea. But let's talk about why I might want to do it. So this is basically, this taxonomy comes from Clemens Vastas. And essentially he said we should divide the world up into messaging and eventing. Right? There's some argument over the name, but let's focus on the division he's trying to get. So message has intent, right? When I send you a message, I want you to do something. Whereas an event provides facts. Something has happened and I want to tell you about it. Typically when we send a message, we're doing one of these things. We're asking you a question. Please can you tell me about this, right? Or I'm asking you to perform a function for me and I'm effectively transferring control to you. I'm saying, please go and take a payment for this order for me. Often, I expect a reply, right? Okay, I took the payment for that order. Sometimes I can do it in a fire and forget way, but often I'm expecting a reply. Typically, when we're doing messaging, we are part of some kind of workflow. We're trying to accomplish something, and in order to accomplish that, I know that you have to carry out the specific task. And there's often a conversation. In other words, there's a dialogue happening. I send you something, you respond to me. With eventing, it tends to be that we have no expectations. Here is a fact. You may choose to do something with it. I don't know. I don't really care. Right? I may be shouting into the void because none of you may care about my facts. Often, it represents history. Somebody asked me to do this thing. I did it. Here is a record saying I did it. Right? Someone asked me to take a payment. Hey, here's an event saying a payment was taken. Right? It may well be a reply to something in messaging. Quite often, it may be giving us context. One thing we typically use a lot of at my current place is event carriage state transfer. Lots of things need to know about restaurants. So we actually distribute that information so you can effectively have a local copy of it. Now, there's a context which you quite often need when you then respond to doing whatever your work is. You may have to look up some of those details for yourself. Okay. History and things you report on, typical use case. Messaging is about the future. It's a proposition about how you want the world to look. Okay. Eventing tends to be about the past. It tends to say something happened. If you're familiar with Gregor Hope's kind of model, you can kind of align that as this as follows. That really the command model is messaging, and eventing includes both document messages, which contain a lot of data, and event messages using as notifications, which basically just contain a signal, but don't necessarily contain all the data. They assume you have it by another means. And further, Clemens went on to divide eventing into discrete and series. So in discrete, typically the model is push, although depending on the actual middleware, you may well be polling for it, right? But typically the model is push, something happens, and I'm going to notify you about it. And typically in series, the model is pull. I want to go and get some data that you have, and I'm going to maintain an offset into a set of data which I'm going to use to basically consume it. Right. Typically, in discrete events, they're entirely independent. In series, they are sequential. So really what we mean is that independent events, we don't really care about ordering, right? This thing happened, another thing happened, another thing happened, but there's no order to them, basically. A payment was made, a payment was made, a payment was made. They're all for different orders. It doesn't matter what order I receive them in. I just need to know that that thing happened and I can react to it, right? Whereas sequential might be, hey, the restaurant basically updated its address, the restaurant updated its address, right? They get them in the wrong order, I'm going to have the wrong address. As a result, these tend to be immediately actionable. This thing happened, I'm going to deal with it. These may not be. You may just be actually accumulating condition about something else's state, and you may choose to act upon that later, or you may choose to use that information when you do act in response to receiving a command. All right. Let's talk about queues and streams, another bit of the puzzle. This is a queue. In a queue, we tend to have a model which I tend to call lock and read past. Okay. So what you'll find is that the first consumer, or a consumer of my queue, what it does is it's aware there could be other consumers of the queue. So it locks a message in order to process it. Any other consumer can now read the queue, but they read past anything that's currently locked by another consumer. That consumer's processing it, right? And they read the next item in the queue. And this locking mechanism is a fundamental part of how nearly all queues work. I mean, they call it different things. SQS has a visibility, timeout, etc. But effectively, there's a locking mechanism, which allows us to then have multiple readers to process an individual queue. When I'm done processing the item in the queue, then I ACK it. Generally, that result in it being unlocked and deleted. Sometimes I may want to say, well, actually, I couldn't deal with it. Typically, that may be that a resource that I depend upon has a transient error, and I can't talk to my Dynamo store right now. I expect that error will clear, and maybe I can do that operation again in a certain amount of time. Or maybe the state of the domain is not quite where I need it to be, but I do expect that it will be there if I just allow time to pass, right? So to do that, I can effectively say, well, I can knack it and put it back on the queue, and typically I can do that with a delay, right? I say, put it back on the queue, but wait a little bit. And then somebody else can then pick it up and process it off the queue. And after a certain number of these requeue attempts, I may decide, well, hang on, we're never going to be able to process this message successfully. What I want you to do is actually, this time, knack it and move it to a dead letter queue. Somebody's going to have to inspect that and figure out what was wrong. Potentially it's poison pill, or potentially, essentially, I've just got a bigger problem at the back end. At that point, typically, if I had a big enough problem at the back end that I was starting to put stuff onto a DL queue, I would probably shut down reading from this queue to avoid moving all of my contents onto the DL queue at that point, right? But typically, you've got some policy that's moving stuff across. So, sorry, that's a little bit down the bottom for those of you in the corner, so I'll read that one. Queues we can think about as containing tasks. With queues, we can think of messages on a queue as tasks. They are a request for us to carry out an action. Once the action is done, we delete the task. We don't want anyone else to action it. It's already been done. Someone receiving a done task would have to discard it, and if we can't action it, someone else will need to action it. Right? So we think about it as a queue of work. Someone's going to action it. It doesn't matter in what order we action it usually, right? We just want to basically make sure it's actioned as soon as possible, and we want to make sure that it will be successfully actioned at some point. Streams work a little differently. With a stream, I read the next message in the queue and I process it, and when I've done, another consumer would simply read the same message. There's no notion of locking. You don't lock an item in the queue. There's no notion of read past, right? You can't read past because somebody else is processing it. You're just going to start consuming the queue from the beginning the same as everybody else does. When you've basically read an item, you store an offset into an offset store, and you say, hey, this is how far I've got. Okay. And you then read the next message in the queue. And the second consumer may then store his offset. But everybody is essentially just reading through, in sequence, the same set of elements and storing their offsets. There is no lock, there's no read past. Okay. Yeah, that's just saying, if a consumer restarts, it can pick up its position from the offset store and resume processing where it left off. Right. We think of streams as containing facts. I'll read this again because it's at the bottom. With streams, we can think of records on the stream as facts. They are records that indicate there's been a change in state. We can view facts as an inverse database that represent how current state is arrived at, state. We can navigate offsets to calculate a position at any point in time. We don't consume facts by reading them, they persist. So essentially, we can think of streams as having these facts. They're not tasks, right? They're not done when we've read them. They exist, they're facts, but we may want to consume them by stepping through those facts and saying, I've seen that one, I've seen that one, I've seen that one, I've seen that one, and managing our offset. So this has implications for how we scale these. We've already seen effectively how we scale queues. We scale them by competing consumers, right? I can just add more consumers of the same queue, and they'll all essentially read past anything that's already locked and process something. Provided those items are all independently actionable, I'm not worried about the fact that I'm doing them out of order, right? They're just work that needs to get done by somebody at some time. With streams, I have to partition them. Right. Given that I read every element sequentially, adding multiple threads just adds more readers of the same sequence. So I have to break it up into partitions, where each partition represents a part of the overall stream. Typically, what I'll do is use some kind of hashing algorithm that says, a consistent hashing algorithm that says, okay, anything to do with the Acme restaurant always goes to partition 1. Anything to do with the food corp restaurants go to partition 2. That means essentially I will preserve ordering, because something for that same identifier always goes on the same partition and will be processed in order. But because I now have multiple partitions, I can have a thread reading each partition, and I can therefore scale up. But different models, right? Queues effectively competing consumers, streams up by partitioning. With partitioning, by the way, just as a kind of help for those that don't know it, you may be worried, well, hang on a minute, if I've only got one thread reading it, what happens if it dies? Am I just not processing anymore? So you create what's called a consumer group. A consumer group says, at most one thread reads from any partition, but effectively what I can do is distribute the work over a number of consumers. So if I have less consumers than the number of partitions, some of my consumers will get to read multiple partitions, right? So if one of them goes down, somebody else can take over, keep reading my partition. When I come back up again, we'll rebalance basically amongst the number of consumers that we've got. You could have idle consumers if effectively you've got more consumers than partitions, which is kind of wasteful, but you could have that, where effectively something would take over if one of them went down as well. Right. So consumer groups help us solve that problem of reliability in a model where effectively we have to basically scale by partitioning. So a language we can think of as a map of the world in terms of basically the way we can think about things. So let's go to commands and events, this old kind of model, right? So when I think about a command's an instruction for someone to do something and usually used as part of a workflow, right? Remember, we're thinking probably in that messaging side of the taxonomy. So I typically would say, I go to Akin and say, make me a cup of tea. That's a command, right? I'm expecting a response, which is a cup of tea. I addressed him directly, not anybody else, right? We know that I've asked him to do it. I didn't just wander around the room going, yeah, kind of like a cup of tea, which would be a fact, but I may have no expectation that anyone's going to get off, leave their chair and go make me a cup of tea, right? So commands tend to be imperative. I've got an expectation that someone's going to do it for it. Akin's a nice chap, so basically, effectively, he's going to do it for me, right? So typically when we think about the type of message we're sending, one of the first questions to ask is, do I have an expectation about who will handle this and do something? Right. There's this thing called passive-aggressive events, is where people think they're doing events, but they know full well that there's only one listener to this event, and that listener's going to take an action for them. They've got a command, they just don't recognize it. They like to think, I'm at least a couple to have events. But actually you have some behavioral coupling because you actually have to use a command in that case. Right? Can be fire and forget or request reply. So fire and forget basically just says, typically where I don't need a response, basically it might be, I need you to leave the room, right? I don't expect a response from you down the corridor going, I've left the room, it's okay, right? I just expect you're going to carry out the instruction for me, right? Whereas a response, well, if I want a cup of tea, I expect a response, right? I expect a cup of tea to come back to me. All right. Typically, you want to use a queue for a command. So messaging in that taxonomy wants to use queues. Because typically, there is no ordering to my commands, right? We may all give instructions for tea or coffee, right? Doesn't really matter, we still want our individual tea or coffee to come back. There's no order to it, there's just basically a sequence of jobs that need to get done for us. Okay. And it's important that they all are carried out, their instructions. We want them to all be carried out, so we want people to retry them if they fail, etc. We may also want to move them to a dialectic queue for someone to inspect them if they didn't happen, to understand basically we may have lost service from a customer. Right? So here's a typical kind of example. We would see a lot. Some sort of purchase comes in, right? We've got some process that does processing purchases, probably does some validation, checks the prices, makes sure that basically we have stock and can do that kind of thing. And part of what it might do is say, hey, we need to take a payment for this. Right. It knows that we have an accept payment service, and that's the thing that talks to our payment provider, right? We're not raising an event saying, hey, this needs payment. We know our workflow is probably not going to complete without basically a response. There's cause and effect here, right? If we drop basically the notion of cause and effect, we have this problem of, I say, well, this thing needs a payment, and then later on someone says, well, we never got a payment for that, and well, we've shipped it already, right? Before I can take later steps, I must execute this step, and there's some kind of cause and effect going on. So I expect that accept payments will take a customer's payment for this order. It's a command, quite clearly, I'm giving you, right? Okay. So what about events? Well, events basically are a fact saying something happened, right? So quite often an event is a response to a command, right? The cup of tea or coffee would be an event, right? You leaving the room is effectively an event, right? They represent something that's happened that you may be interested in as a result of work occurring. Okay. If it's a request reply, typically we have a correlation idea. If I go into Starbucks, they say, what is your name? And they write my name on the cup. They don't care what I say as long as it's roughly unique. We can all do the I'm Spartacus gag and put Spartacus on our cup. They don't care. Why do they need it? Because at the far end, because Starbucks uses messaging, right? They write the message on the cup, it goes to the barista, runs the process, basically making your drink, puts it at the far end. That is my reply to my command to make a coffee, and I correlate my request with the response by the name. So the name acts as a correlation ID in Starbucks to say, this is the response to that request for a drink. So typically, in a messaging scenario where you want a response, like an event, to say this is a response to that command, you need to have a correlation ID, because this service will just have basically stored some state saying I'm pending a reply. Right? When it gets the reply back, it will look up basically with the correlation ID and says I can move this workflow on to the next step. You're running some kind of state machine quite often when you give commands, right? So, eventing could be serious or discrete. Right, so typically, if it's a reply, I tend to quite often use thing that is pretty suitable for discrete, right? So potentially be handled by a queue. I want to read that off and deal with it. There's no ordering to it. Doesn't really matter what order they come in, right? Just need to make sure that someone knows that that happened and has recorded the data and moved the state machine on. Okay. Or a stream. Typically, a stream would be we care about this basically in some long-term proposition. So. You've left the room, and effectively we care that basically, you know, someone has left this room, and because we're monitoring room access, right? I'm sure these secret armbands they gave us are doing something that we don't know about. All right. So typical example again, right? The purchase order was raised, we processed purchase, we told accept payments to basically take a payment for it. So typically one way it might respond is say payment accepted with an ID, so I can then move this on and say, great, I'm going to raise an event saying the order's been purchased, because that workflow is now complete. An error would just be a different type of event, right? Payment was rejected. Card basically was declined, right? So it's just another path, right? Just a different type of event, and I would listen to that event and say, oh, rather than moving that to the order purchased, I probably need to raise a different event which basically tells the customer to present a new card. Right. We discussed that, right, yeah. Typically, this status update might be serious because things listening to that may well want to be recording order history for us, right? This may also, by the way, at this point, issue another command to move us on to another process step and workflow. Okay. So a slight tangent, just because the context makes it easier. A lot of the time in messaging, you see stuff like this floating around, right? It's a purchase order, it's got the customer name on it, it's got the restaurant name on it for where I currently work, right? And there's a problem here, and that's that basically these items, they don't belong typically to the process orders process that raised this message. They have a different lifetime, I don't own them. If they were to change their schema, that would basically ripple through to me having to change my schema, because essentially I now have that as part of my message schema. And they tend to bloat these messages and make them large. And we can think of these as being transitive dependencies, right? I have a dependency on customer and on restaurant now as in my purchase order message, even though my purchase order message is really nothing to do with those domains. I now have a dependency on them, basically. So what do we do with transitive dependencies? Well, so we do the same thing in messaging we do in databases, which is effectively you replace it with an ID. So we have a customer ID and a restaurant ID, right? And we say, this purchase order is for this customer in this restaurant. And what we expect you to do is go away and look up the customer or restaurant that purchase order was for, rather than putting it in the message. To avoid you having to make a get, right? We don't like gets between services if we can avoid them. But to avoid you having to make a get, what we do is effectively we use event carried state transfer. So we say, actually, you should listen to messages from the onboarding customer service that will tell you about changes to the customers, and you should listen to messages from restaurant onboarding that will tell you about changes to restaurants, and you should build a local lookup table to look up that information. And then essentially you can effectively do the join to those IDs locally yourself. Okay, that's what event carried state transfer is. We use that a lot. This is not a talk about event carried state transfer, but I want you to understand kind of how it works, because so the idea is basically this overall process is going to listen for upstream events for things like restaurants, customers, right, as an example. It's going to basically take that data. Typically, this is series data, because a series eventing data, because it tends to be sequential and ordered, and I'm using it for later analysis. And it's going to essentially insert that into a lookup table, so when I get so I can do joins, right, which removes the need to do gets. Now, if I think about how a queue works, when I read from a queue, I delete items in a queue. And that means I don't have what we call archive and replay, right? Those messages are done. There's no way for me to look at those messages again without the sender resending them, and that's desirable, right? You've done that work. We don't want to resend it. We'd have to basically figure out we've already done this work and discard it. Okay. Streams, though, of course, basically just an offset, right? So it isn't necessarily deleted. Now, your messaging middleware may decide to delete elements on queues after a certain amount of time has elapsed that you can set, but in theory, some of them, like for a Kafka, you can have infinite retention, so you can keep it forever. So these support archive and replay because I can always go back and replay the stream that I had. So if I think about something like ECST, I'm obviously going to want to basically have a stream, because I may want to blow away my local cache of your data and rebuild it for whatever reason. Maybe I made a programming error on my side, maybe there was a failure, or maybe I'm just introducing a new service that wants to start reading restaurant data and has to catch up with history, right? Needs to initialize its cache. How's it going to do that? Am I going to resend everything over a queue? So on a stream, just pick it up, right? So archive and replay here would mean that effectively we can just rebuild the cache on demand. Requeue and delay. So as we looked before, queue support, requeue and delay, right? This idea effectively I can say, hey, put it back on the queue, and then put it back on the queue with the delay so that I can choose some transient error. Streams do not support requeue or delay, right? There's no way of doing that. There's no lock and making things therefore available or not available. Typically you see workarounds to this problem in some places. They will copy the item they want to requeue to another queue and poll that at a higher interval, such that basically they introduce the idea of basically there being delay. And similarly with the dead letter queue, they will effectively, if they can't process it, move them to another topic which they call a dead letter topic, right? They are trying to emulate the behavior of a queue. The reality is they should just have used a queue. Whenever you see people effectively building that stuff, it's usually a consequence of the fact that they have done something like said, we only have Kafka, right? And they now have to try and rebuild all the queuing semantics on top of a stream. And the simpler answer would have been to use a queue alongside the stream. Okay. All right, so a sort of summary of this section would be messaging, as in messaging, basically the taxonomy, so commands, typically you want to use a queue and not a stream. Okay. In terms of eventing, discrete events, one's effectively where I can immediately action them, ordering is not important, etc. I could use either. Series events, one where sequence is important, I may want to manage my offset and pull, you basically want to use a stream. Generally, queues are not so good for ordering. You can get FIFO queues, etc. They come with all sorts of limitations. The problem with queues is the very nature of queuing makes that complicated, and you're effectively that people are building effectively a stream technology over a queue. So you can get SQS FIFO queues with effectively consumer groups and stuff, but they're effectively trying to build streams over queues. So it's a little bit unsatisfactory. It does work, but it's not great. Archive and replay, you're essentially going to want a stream. And requeue with delay, you're essentially going to want a queue. And you can see that depending on what you want to do, you need to pick either a queue or a stream, but they have quite different characteristics. All right. I seem to be about on time. Okay, cool. There are other things to consider, and that's that we may choose to go beyond doing routing. Okay. This is basically stream processing. So stream processing answers the questions, how do I join data now it lives in independently deployable microservices? Right. So if I have all my microservices and they have data and I want to make a query across them, how the hell do I do that? Typically what we want to do is have that microservice expose basically a stream or one or more streams that basically contain facts that represent state which I'm willing to externalize from the microservice. So it doesn't have the same shape as my inside data, but because it's an external contract, but it's basically what I'm willing to share with you and commit to some necessary coupling over that contract. Right? So I share that to the outside world. And we can think about that as being a kind of inverse database. Right? Databases essentially give you a table based on a effectively transaction log, a series of things that happen, arrives at basically the current state of the table. So with a stream, which represents an ordered sequence of events, something that happened, I could treat it like a transaction log, and I can effectively reconstruct a table. I just have to tell the window during which basically I want you to build the table over in terms of time or timestamps or records, right? So between here and here, build me a table, tell me what the position looked like. Or I can have a real-time table, which effectively is continuously being updated, right? And that table then allows me to then write queries. Typically, when I write those queries and want to produce a result, I'm not producing some, a record set that comes back over ODBC, or like I'm effectively going to produce a new topic, and the new topic's going to have the results of that. Right? So a new stream. So effectively, I can aggregate and filter these streams and produce a new stream with results. And that is, for example, what you'll find in Kafka, when essentially you do stream processing by using things like streams, applications, or KSQL. And these aspects are quite powerful additional properties that this kind of middleware gives you that you don't get, say, from something like RabbitMQ, because RabbitMQ was focused originally was focused much more on doing queues. It's got some streams now, but because they're not looking to solve this problem. So that's one of the nice bits of Kafka, but doesn't mean that Kafka is what you want for everything, right? Okay. And in addition, the other thing you may find is once you get into that kind of world, then Kafka and others also basically have this model which says, well, I may not have in every case a good source of basically events to act as my topic. And for legacy, third party, or simply work pressure related reasons, I may not have time to produce a decent stream. What I can do is potentially hook up something that knows how to listen to my database effectively, and as it sees rows being written to my transaction log, turn that into events. Listen to something that basically is, producing an atom feed over HTTP and turn that into a topic. And these connectors, so in Kafka you have a thing called Kafka Connect, can let us effectively create streams which we can then pass through basically aggregate and join. And we can effectively then use a connector at the other end at the sink to put it somewhere, like a database, etc. So typically one of the things with event carrier state transfer we referred to earlier, you may want to do is have sources that expose streams. Here's the stream of restaurants, here's the stream of customers, right? Listen to that, aggregate it if you need to, and then you can basically stick it in a data store at the far end where I can basically have a copy of that, which I then use as my lookup table. So you can automate much of the production of that event carrier state transfer nowadays. days. Okay, cool. Almost there. We're going to look at environment briefly. Okay. The other thing that will influence your choice, besides all the sort of more technical factors, is what is actually available, right? And that depends where you're running. So Kafka, Rabbit, and ActiveMQ were really originally designed to run in racks. They have got much better at running in cloud environments and running in cloud native, container-based environments than they used to be. But they were originally built for running, on a rack with very few network partitions, because basically they had tiny short cables on the rack, right? And then when we start running them across multiple availability zones, they all started to fall apart, but they got a bit better. If you're running in a rack, though, you are limited to those choices, really. Or really expensive stuff like TIBCO, which I won't mention, because if you can afford it, you can afford it, right? On the cloud, generally most of the cloud providers have their own equivalents, right? So Amazon, the queuing technology is SQS with SNS for routing if you need it. The stream technology is Kinesis, right? Azure Service Bus is the queuing technology, and Azure Event Hubs are the streaming technology. And Google PubSub is effectively only does queuing. There's a color code there in case you basically didn't realize. Containers, in the container world, we've actually seen more of a move to technologies to support both queues and streams. So Nats and Pulsar both have recognized this problem, and this generation of tools is starting to say, hey, you may want a stream, you may want a queue. I assume you're going to pick whichever one actually fits your use case better. And it's probable that gives some of these an advantage at the minute if you want to start thinking about being more polyglot, because you don't have to know multiple technologies, which reduces the cost, effectively, of a polyglot approach. In other words, saying, hey, I need streams and queues. This supports both. It's a bit like, databases began to support basically key value as well as relational models, etc. Right? So that may be an easy route. The thing you will miss, and the reason you may want to have more, is because, of course, when you begin to think about things like stream processing, right? So complex event processing models, if you want stuff like KSQL, Kafka Connect, you may want to go back over here, right? And you'll interesting to see things like RabbitMQ has started to get streaming technology inside, and so that may change people's perception, that you may find more of these begin to ask the question, do I need to support both? I don't expect the cloud providers to support both in one product, because they just have multiple products right already. Makes sense? All right. So really to return to the kind of point of my talk originally, my advice is that you should think about the characteristics of what you are doing and then pick an appropriate technology. You should decide if you are doing messaging or eventing, right? Commands or events and documents. If you're doing messaging, you want to pick a queue. If you are doing eventing, you need to decide whether it is basically discrete or series. If it's discrete, you can choose either. You may want to think about, if you're using a response to something that's basically messaging, it's probable that it may make sense to actually then respond via messaging as well, right? Using the same middleware. But if effectively you are just raising facts for the rest of the world, you may want to basically consider thinking about that as being series. Right? And that when we think about queues and streams, then recognize that they're supporting those activities by having things like requeue with delay and competing consumers for just doing the whole set of work style jobs in a queue, or archive and replay and partitioning for when I'm thinking about distributing data, which you may want to then basically take into some kind of store at your end and then use for context for performing your own operations. Okay. And that will give you a better model than just saying, I'm going to put everything over Kafka, or I'm going to put everything over RabbitMQ. All right, that's me done. I think, have I got 5 minutes for questions? I have to hand you the mic. Have I got 5 minutes or?
Yeah, we do. We do have some questions. Help with the microphone.
Excellent. So you presented a very clear difference between queues and streams. Do you think there's a scale at which it becomes impractical to use queues, even though you get like nicer semantics, and you have to fall back to using streaming technologies?
It's a good pause, isn't it, for reflection? We haven't hit that, and we do, you know, hundreds of thousands of orders in a given evening in our busier market, sometimes even millions. And we use queues for much of that ordering capacity. So we haven't seen it, and I don't think that it represents a particular problem that you would use a queue to do that. But it's a good question. So I'm not saying no, I'm just saying I haven't seen that yet.
Sometimes maybe a choice becomes more, or maybe developers become more confused because some technologies give sort of blended choice. For example, if you take Azure Service Bus, there is Azure Service Bus queues and there is topics. And I've seen that some teams, they were using queues for messaging while topics used for eventing. Because, okay, you have multiple subscribers to this topic, while probably judging from what you suggest, we should, in that scenarios, use Azure event hubs, which they also offered. So what do you think about using like things like Azure Topic Exchange for event?
So don't forget, eventing has both a series and discrete model. So on a discrete model, you might want to, you could possibly use the Azure topics basically for that kind of discrete event model quite successfully. I think if I was distributing data where I wanted things like archive and replay, I wanted multiple people to be able to effectively read it, reset their offset if they wanted, read it again, I would move to streams. There's a difference between, if you like, pub-sub distribution, where you're essentially saying I've got many listeners to a given event, but effectively once they've done with it, right, that event is gone, and saying I've got this persistent stream of data where I can go back and forth basically on demand, which is much more that streaming technology.
Okay, any more questions? I see. Okay, thank you very much. A round of applause for Ian. One more question. Okay, we do have a few more minutes.
A quick one. Sometimes also like event can be treated as a command. For example, if speaking about a coffee shop, we have event, we run out of coffee, and a related command: buy more coffee, purchase more coffee, and then a team can choose like to easy way out. Like we just subscribe in this event, and then and we generate some internal commands. Alternative would be to actually we have some adapter which will generate like queue message for buying. So how careful, I know of course the answer probably depends, but like from your experience, how strict should we about like on this adapting events as commands?
All right, so at the end of the day, I am sending a message, right? Be it a command or an event. So why is that semantics important to us? Well, a couple of reasons. One is technology choice, but the other is understanding what I as the sender am doing. So if I as the sender have a workflow where effectively I have a step in that workflow that requires cooperation with somewhere else, I have to effectively do some orchestration. Now I would tend to persuade you not to do orchestration in some external orchestration engine, right? Some Saga event. I'd say most cases you just want to do it actually locally to the individual service, where effectively it says I need responses from others in order to complete my workflow. So the thing to do is to think about it being workflows, right? To take the example you're raising, right? So the coffee shop runs out of coffee. Okay, so generally what's probably happened is a coffee machine or whatever effectively has indicated that basically it's out of coffee. The coffee machine itself doesn't care about the fact that basically no one may be listening to it, right? It just says, I'm out of coffee, I'm going to stop working. That's its lot in life. Its job is to basically make coffee. Well, when a button is pressed, it makes coffee, or it signals an error, right? So you could say, well, it's an event because the coffee machine itself doesn't care. It's not going to do anything as a result of it. It isn't going to run the workflow for ordering more coffee, right? Typically somebody else will get that, and as you say, effectively, we would then order more coffee. Now, it's a 0 or more thing. So, right, we could have a situation where if the coffee machine is not hooked up to any kind of automatic reordering process, then I have to wait for somebody to notice the blinking light that says it's out of coffee, effectively, and initiate the other process. If no one notices, I could keep going, oh, I keep being out of coffee. I mean, sometimes you go to a hotel and you're at breakfast and you can't find a coffee machine that works, right? Because it's event-based, and until someone notifies someone that event, the coffee machine can blink its lights all it likes, until one of the staff gets told, no flow happens. So it depends how much you care. Because you could conceive of another model which says the coffee machine notices it's going low, it has a workflow built in to reorder coffee automatically, which is where we get with a lot of IoT stuff, right? Where we're effectively saying, well, why do we need a human being? Or the coffee machine can basically just initiate the get me more coffee process, right? Which may appear as a ticket in somebody's item, go to the store effectively and please get more coffee out and fill coffee machine number 3, right? So you could have a command, so a little bit depends on how does your business want to handle that model, right? Does it want a coffee machine to be smart, and I say I'm going to operate a workflow to solve the problem? Or does it want the coffee machine to be dumb and say it's going to signal something else, pick the workflow up and handle it? And so it is an it depends answer, but hopefully it's a bit more specific than just it depends.
Okay, so now we really ended the session, and I invite everyone to go grab some snacks, continue chats with Ian if you would like. Oh, of course, don't forget to fill in your bingo cards and visit all the partners. You can get some awesome prizes.